just going to look at trig substitutions today. So when we've got these sort of integrals that involve square root signs. So if we can use our trig identities to turn two terms into one. So if we have something like a squared plus x squared, I can use x equals a tan theta, and that'll turn that into a squared plus a squared tan. Square root of that would be a sec. A squared minus x squared, which I would use either a sine or a cos. Doesn't really matter. Can you get a squared minus a squared, say, for instance, sine squared becomes a cos. And the other way around, x squared minus a squared, and I'd use a sec to simplify that one down. So 1 on the square root of a squared plus x squared. Yes, I know this is one of our standard integrals, but we'll use this idea to go and prove that standard integral. So a squared plus x squared, use the substitution a tan theta. That gives me dx is a sec squared theta to theta. So substituting in a sec squared theta to theta on the square root of a squared plus a squared tan squared. Well, that's a squared sec squared. Square root of a squared sec squared is a sec. Cancels with the a sec squared on top, leaves me with sec. And you'll remember that the integral of sec is the log of sec plus tan. But of course that's in terms of theta, so I need to get the x's back into it. So what I then do is draw myself up a little triangle, and I know that x over a is the tan of theta, so therefore the hypotenuse will be the square root of a squared plus x squared. Now it's no coincidence that that third side turns out to be the square root we started with, because we're using the Pythagorean trig identities. So of course when I use Pythagoras over my triangle, I get the same expression. Substituting in, I get log of the square root of a squared plus x squared on a plus x on a. You'll notice that's not the standard integral. But log of a, because remember this is all over a, I can use my log laws to take the log of a out, but log a is just a constant anyway. So we can still say just plus some constant. X on the square root of 1 minus x squared. Now I probably wouldn't use a trig substitution to do this, and I hope you wouldn't either, because I hope you've noticed it straight away. The x is on the top, and the derivative, of course, of minus x squared is minus 2x. That would be a lot quicker. But let's use the trig one to show that, yeah, we could use this technique. All right, so x is sine theta, dx would be cos theta to theta. So we get sine theta cos theta to theta on the square root of 1 minus sine squared. Square root of 1 minus sine squared would turn out to be cos theta, or square root of cos squared, which is cos. Cancels with the cos, and we've just got the integral of sine theta. Integrate sine, we get minus cos, and so once again I can draw up my triangle. Sine is x over 1, so adjacent becomes the square root of 1 minus x squared. Subbing back in, and there's our answer, minus the square root of 1 minus x squared, plus, of course, a constant. Square root of x squared plus 3. So this one I'm going to use tan for this one. So it'll be root 3 tan theta. The derivative is root 3 sec squared. Oh, yuck, sec cubed. That's the one we've got to do by parts. Remember the odd powers for sec, we end up doing by parts. So we've simplified this down to be 3 times sec cubed theta to theta. So the sec cube will break into sec theta sec squared. I'll do u is sec, so we get sec theta tan theta for du. The v is sec squared, so v becomes tan theta, but it's 3 times all this. So 3 times uv, sec theta tan theta, minus 3 times sec theta, the integral of sec theta tan squared theta. The tan squared I can now rewrite as 1 minus sec squared, and that creates these two new integrals. That's where we've got to be very careful. I'm not going to equate with the very first line at this stage, because that's the square root of x squared plus 3. I'm going to equate with the 3 sec cubed. So I end up with 3 sec theta tan theta minus 3 times the integral of sec cubed plus 3 log sec theta plus tan theta. Although I suppose I could say I know that 3 times the integral of sec cubed theta is the square root of x squared plus 3 and do a substitution in there. Square root of x squared plus 3. So I did do it that way. So I've substituted in for the 3 sec cubed theta. So be very careful with that, because it's not sec cubed, it's 3 sec cubed that I'm substituting in for, which happens to be the same as I've got here. And then for the sec theta, I've got the square root of x squared plus 3 on root 3 times tan theta, x on root 3, and then the log of sec plus tan. I'll move the integral to the other side. So I've got 2 times the integral of x squared plus 3. I probably did I? Divide everything by 2? Yeah, I still think this looks a bit ugly. The log of the root x squared plus 3 on root 3 plus x on root 3. Yeah, I got rid of it. I just incorporated it in the constant. Looks a bit neater. Oh, no. If you leave it all over square root of 3 inside the log, it's the same answer. That's just the enjoyment we get having to mark the questions. It might not be the answer I'm expecting, but it may still be correct. So.
Do we have to write like a new constant after we...
Nah, it's not that big a deal. I mean, if you really want to, I suppose you could change it to plus k because it's a different constant, the constant in the line before. But the only time I suppose you've got to be careful with that is if you're doing calculations with the constant, then you might need to. All right, so exercise half a jolly good fellow from Patel. Yes, yeah.